Hello, everybody, and welcome to lesson 7.8 for Math 9. Today, what we're going to talk about is something called rotational symmetry. In layman's terms, all rotational symmetry is how many times you could rotate something and it still looks the exact same as when you originally had that object. All right, so for instance, if we just jump into this first example, we have this shape right here. It's a nice, simple cross, this guy right here. If we looked at that, if we were to spin that thing, let's say 90 degrees, then it would actually look the exact same, right? Like if we took that and we spun it so that the top was on the right side was now on the bottom was now on the left side, and the left side was now on the top, the object would still look the exact same. That's what rotational symmetry is. It's how many times you could do that and it still looks the same. Let's look at the first one. So if you look at the first one, I could rotate this 90 degrees, right? And that object looks the exact same. I take that original object, I rotate it 180 degrees, so the top is now at the bottom. It still looks the exact same. I take that object, I rotate it 270 degrees. Now the top side is on the left. It still looks the exact same. And if I took that object and I did a full 360, it comes back to the original spot and it looks the exact same. That means this thing has a rotational symmetry of order 4. Sometimes we call that order of rotation as well. So the order of rotation equals 4. Same thing, rotational symmetry, order of rotation, kind of interchanges words. They're kind of like synonyms. Awesome. There is a formula to figure out how often something will be the exact same. There's also a formula to tell what angle you need to turn it to make it the same. So in general, this is the rule. Okay, now it's not always true, but in general, if you were to want to figure out the angle at which you have to rotate to get symmetry, so the angle of rotational symmetry, what you do is you do 360 degrees and you divide it by the order of rotation, which is the number of rotations. So for instance, if we wanted to figure out, okay, what angle do I have to rotate this image so that it looks the exact same? That's the angle of rotational symmetry is equal to 360 degrees divided by the order of rotational symmetry. That's how many times it will actually look the same. If I replace that with 4, that means we have 360 degrees divided by 4. That's 90 degrees. And what that's telling us, the angle of rotational symmetry, is that every 90 degrees you rotate it, it'll look the exact same. It'll look symmetrical to what you started with. And we see that that's true if we look back up at the original image. We rotated it 90, it looks the exact same. We added 90 to get 180, and it looked the exact same. We added 90 degrees to get 270, it looks the exact same. We added 90 degrees to get 360, it's the exact same. So this did work, the formula. Angle of rotational symmetry equals 360 degrees divided by the order of rotation. Just for the record, you could also rearrange that formula. So you could rearrange that formula if you ever wanted to figure out the order of rotational symmetry, like how many times something would look the same. You could just do 360 degrees and divide it by the angle that you have to rotate to get the same thing. Beautiful. One more thing, just for the record, is that we don't ever have something that's a rotational symmetry of order 1. That just means that it's not the same, right? If something does a 360, of course it looks the same. So if that's the only way it looks the same, we just don't say it has a rotational symmetry. We say it does not have rotational symmetry. We wouldn't say it has a rotational symmetry of 1. That doesn't make sense. We just say there is no rotational symmetry. Perfect. Let's look at another example. So we have a pentagon here. Pentagon's a 5-sided regular pentagon, means that the angles in the side lengths are all the same. If I took this shape and I spun it around, and I spun it so that this corner was now in this corner, you would still have the exact same shape. For our note's sake, what they do is they put a little dot in the one corner to show how the corners are moving. So this corner, when I rotated it, turned out to be over here. And if I rotated it again, the shape would still look the exact same, but the dot would now have moved to the top left. We could rotate it again, and the dot is now at the top. We could rotate it again. The dot is now on the right-hand side. Oh, sorry. Awesome. That means that this shape has an order of rotational symmetry of 5. Because there's 5 different ways I could make this pentagon look, and it's still the exact same, right? I could have the dot in the bottom right, bottom left, top middle, top right, but the pentagon itself looks the same all the time. Figuring out the angle that I'm rotating is hard because it's not really doing a 90-degree turn. It's not doing a 180. It's kind of like doing a weird turn, right, to get from corner to corner. The way we figure out that angle is by doing the angle of rotational symmetry equals 360 degrees divided by 5. 5 because there's 5 different positions that would look the same. If you put that in your calculator, that means the angle of rotational symmetry is 72 degrees. That means for every 72 degrees, we would get these angles. Perfect. We're going to do a couple questions and we're going to be done. So example 1, what is the angle of rotational symmetry for a shape with order of rotational symmetry, with each order of rotational symmetry? Whenever I do a question, I try to figure out what it is I'm looking for. The question said, what is the angle of rotational symmetry? So I'm looking for the angle of rotational symmetry, ARS. I know that ARS equals 360 degrees divided by ORS because that's our formula. We're going to use that formula for the 2 questions that they gave us. All right, the first question said that I had an order of rotational symmetry of 4. That means my ARS equals 360 degrees divided by 4. If I put that in my calculator, that means it's 90 degrees. That means every 90 degrees if I rotated that object, and I don't even know what that object looks like, but every 90 degrees, it would look the exact same when I rotate it. This one over here is giving me an ORS of 10. So I'm going to put that into my formula. My angle of rotational symmetry equals 360 degrees divided by 10. That means that there should be 10 different ways I could rotate that to make it look the exact same. That means ARS equals 36 degrees. So every 36 degrees that I rotate that mystery object, it would look the exact same. Perfect. We can go the other way. So this question now says, what is the order of rotational symmetry? The order of rotational symmetry equals 360 degrees divided by the angle of rotational symmetry. If we put that into our formulas, so I have an angle of rotational symmetry of 30 degrees. That means ORS, the number of times it would actually look identical, is 360 divided by 30. If you put that in your calculator, you should get 12. That means every 30 degrees I rotate it, it'll look the exact same. And there's a total of 12 times I could rotate that object to make it look the exact same. If we do this one over here, we have 180 degrees. That means ORS, the number of rotations that it would look identical, would be 360 degrees divided by 180 degrees. If I put that in my calculator, that means the number of times that I could rotate it and it would look the same is only 2. Right? I could rotate it 180, it would look the same, and then another 180, it would look the same, and then I'd be done. Awesome. We got a few pictures down here. I'll do the first one, A with you and B with you, and then you can try it on your own. So if we look at A, The first question is, does this thing have rotational symmetry? Could I rotate that and it still looks the exact same? And the answer would be yes. I could rotate this so that this arrow is in this spot. This arrow looks identical. It would be in this spot. This arrow looks identical. It would be in this spot. So yes, I could rotate that thing. To figure out the ORS, we're just going to count it. So I'm going to imagine I'm this arrow right here. Okay, so that's 1. If I rotated it up here, that would be 2 spots that are identical. I could rotate it over here. That's a third spot that it would be identical. So the ORS is 3 because there's 3 different spots I could rotate this image. The ARS, the angle in which I'm rotating it, is 360 degrees divided by the ORS. In this case, it's 360 degrees divided by 3. If we put that in our calculator, you should get 120 degrees. That means these rotations that I'm doing are 120 degrees each. And then to get back to the original spot would be another 120 degrees. Awesome. I'll do C with you, and then you can try B and D on your own. So we got a snowflake here. We have to ask ourselves, does this thing have rotational symmetry? It does. So if I was to put a dot, let's say on this snowflake right here, if I rotated this object so that it was in this spot, it would look the exact same. All the sides have a match to it, right? If you're really struggling with does this thing have rotational symmetry, sometimes what helps is if you imagine cutting the object in half. So if I cut this object in half, does it look identical on one side as it does on the other side? Sometimes that helps for those hard ones where it's like, oh, I can't tell if it's rotational symmetry or not. Now that trick doesn't always work, right? Like if I look over here, my recycling thing, if I cut that in half, it doesn't look like it would be working, right? It doesn't look mirrored. But just on questions where it's really hard to tell if something would have rotational symmetry, cut it in half and then see if that worked. That could be like your desperation move. So this thing, I would say yes, it does have rotational symmetry. The ORS, how many identical images are there? Well, there's one there. There's the first red dot, then the second red dot. I could then move that over here to be the third spot. I could move it over here to a fourth spot. I could move it over here to a fifth spot. I could move it over here to a sixth spot. And I could move it back to the original spot, but I already counted that. So that means I have 1, 2, 3, 4, 5, 6 different dots, 6 different spots that I could rotate to. The ARS, the angle that I have to rotate to get it to look the exact same, is 360 divided by 6. If you put that in your calculator, you should get that it's 60 degrees. That means every time I rotate at an angle of 60 degrees, I get the exact same image. Perfect. I want you to try these two. So does it have rotational symmetry? Yes or no? So pause the video and give it a shot. All right, hopefully you did that. You attempted these 2 questions. I'm going to talk a bit about B because B is kind of tricky. If you look at it, people are usually tempted to say yes, there's a rotational symmetry there. It depends what the question's talking about. The picture itself does not have a rotational symmetry. The reason it does not is people envision that, hey, I could take the Ferris wheel and I could move it one spot over, and so on and so forth. However, we're not rotating just the wheel, we're rotating the entire image. And if I was to rotate this entire image, then that means the bottom, the stand down here, would look mightily different when I rotate this entire image, right? This triangle would rotate up here. So now I have a triangle that looks like this. And it's not in the same spot, and that image does not look the same. So this technically, in my opinion, has no rotational symmetry. However, if they wanted to talk like in a question on a test about the rotational symmetry of the wheel spinning, so they would give you more context to the question, then you would say, yes, it does have a rotational symmetry. That's just the wheel itself. That's not including the stand. You're imagining that the stand stays still the whole time. The stand being this silver part right here. Okay. So if we're imagining this is a real life context, we'll say yes. And then I'll calculate the ORS and the ARS for you. I'm going to put up here, does it have rotational symmetry? I'm going to say no/yes. On a test, there would be more context to what they want you to look at. So I could have bought either argument if you wanted to really talk about it. But on a test, it would be more specific. We're going to get the answers for yes, just so you can see what it looks like. So the ORS is how many times you could rotate it and it still looks the same. So I could start in this carriage right here. That's 1. I could rotate to there for 2, to here for 3, to here for 4, to here for 5, to here for 6, to here for 7, to here for 8, to here for 9, 10, 11, and 12. That is a rotational symmetry of 12. There's 12 different spots I could rotate this thing and it looks the exact same. To figure out the ARS equals 360 degrees divided by the ORS, which is 12. 360 divided by 12 gives you an ARS of 30 degrees. Wonderful. Let's look at this tire. So if you look over here, does this thing have a rotational symmetry? I would say yes, it does. We'll try that again. I was trying to do it with shapes by accident, and then I just tried to keep going with it. Yes, it does have rotational symmetry. The reason why it has rotational symmetry, if I imagine there's a dot on the end of this spoke, if I rotated it one more round to right here, the entire image would actually look identical. I could then rotate it again to this spot, then again to this spot, and so on and so forth, for a total of 1, 2, 3, 4, 5, 6, 7 different rotations where that tire looks like it's in the exact same spot. The angle of rotational symmetry equals 360 degrees divided by the ORS, which is 7. That means the angle of rotational symmetry for this thing is 51.4 degrees. Wonderful. I hope you enjoyed our thrilling Unit 7. This is the last lesson, so good job getting through it. You got 2 units left, Unit 8, Unit 9. Best of luck. I hope I see you sometime soon in the future. Reach out to one of your teachers if you need anything, if you want to talk, need some help, if something's going on in your life. We are here for you. Take care.